Okay, so this is where we stopped on Wednesday. We're talking about the highest occupied molecular orbital of the diene and the lowest unoccupied molecular orbital of the dienophile. And so that's what we're looking at here. Excuse me. And remember that the point of this is that the highest occupied molecular orbital is those are the most reactive electrons, the highest energy, and they're going to react with the lowest energy molecular orbital that's available that's unoccupied. And so we look at the HOMO, which in this case is pi 2, and the LUMO, which on the right side is pi star. Those are the two orbitals that are going to react during this Diels-Alder reaction. So that gets us to understanding how the orbital symmetry helps this reaction occur. We can see here that the HOMO and the LUMO have the proper symmetry, the proper orientation for these orbitals to overlap and create bonding interactions, and that's what creates this this reaction to make this concerted cyclic reaction. So this is kind of where we were looking at the end of class on Wednesday and trying to explain what we call the endo rule. And so when we look at these molecular orbitals, we know that where the dienophile is, those two orbitals on the dienophile are going to react with the two orbitals on the end of the diene, right? And so we have to remember the orbital symmetry from our molecular orbital diagram to understand why these bonding interactions occur. But when they do, we're always going to get a specific stereochemistry. So this is a stereospecific reaction that always gives us the endo product. And so here's what we mean by that. If we have two molecules of cyclopentadiene, then one can serve as the diene and one can serve as the dienophile. And so cyclopentadiene, which is just one molecule, it's a pure substance, it will react with itself under the right conditions to create dicyclopentadiene. It undergoes a Diels-Alder reaction with itself to become this dimer product where we have two of the same molecules coming together. But when they do, we're always going to have the same stereochemistry, which is that the group containing the electron withdrawing group, or that double bond, is going to end up in the endo position, and the other groups on that dienophile, the H's in this case, are going to end up in the exo position. So that group that has the double bond will always be endo. And so here is one example of that. We have our diene here is cyclopentadiene. It's the same one we were just looking at. But now our dienophile has this carbonyl on it. Sorry, I have to keep shushing my kids. This second double bond here is part of the pi system. So when we make the molecular orbital diagram for our diene, we have 4 molecular orbitals because we had 4 atomic orbitals going in, right? We had the 4 p orbitals on our diene, and therefore we had 4 molecular orbitals. And because we had 2 double bonds, we had 4 pi electrons, and those 4 pi electrons fill up the first 2 orbitals in our molecular orbital diagram. When we had previously looked at the dienophile, we were considering something as simple as ethylene, which just has 2 carbons, and it has 2 p orbitals, and it has 2 pi electrons. So when we're making that molecular orbital diagram for ethylene, it only had 2 molecular orbitals instead of 4. But now if we look at this dienophile in green on this page that we're looking at here, this dienophile has 2 double bonds, and therefore it has 4 p orbitals. One on the carbon on the end, the next on the carbon it's double bonded to, another on the carbon in the carbonyl, and another on the oxygen in the carbonyl. So there's 4 p orbitals. So what that means is that our diene in blue has 4 p orbitals, which is going to give us 4 pi molecular orbitals. But our dienophile in green also has 4 p orbitals. So it's also going to give us 4 molecular orbitals. it also has 4 pi electrons, just like the diene. So what that means is that the molecular orbital diagrams for these two components are going to be exactly the same. They both have 4 pi molecular orbitals, they both have 4 pi electrons, and so they're going to look exactly the same. The difference here is that it's still the diene that's going to serve as the nucleophile, so it still has the highest occupied molecular orbital, in blue. In green, that's going to serve as the dienophile, and it has the lowest unoccupied molecular orbital because of that electron withdrawing group. The carbonyl in this case is serving as an electron withdrawing group, which is lowering the energy of the pi star orbital on our molecular orbital diagram to make it the LUMO. So, having said all of that, what we're looking at now is we're still concerned with symmetry when we look at these two diene and dienophile and their molecular orbitals, but we're concerned with the symmetry now not only of the two carbons that are going to be making those bonds. We see those dotted pink lines on the far left. We're interested in the orbital symmetry of those two carbons on the green compound, but we're also interested now in the orbital symmetry of the carbonyl, the C double bond O, because there are other orbitals there now that we hadn't considered before, and it's the effect of those other orbitals that are going to cause the endo rule. So the reason that group always ends up in the endo position when there's a double bond in the dienophile, it always ends up in the endo position because we can see here in the middle this transition state. Not only is there orbital overlap where all the pink dotted lines are, those are definitely overlapping because that's where the new bonds are forming, we also have overlap between the carbon in the carbonyl and those carbons on the diene that are not forming new bonds, right? So we see those pink dotted lines between the pi orbitals on the diene in the transition state, indicating that that's going to become a double bond, but it also has the same symmetry as the carbonyl carbon on the bottom. So right there where it says secondary overlap, that's because the symmetry of the pi orbital on that carbonyl is the same as the symmetry of the pi orbital on the diene. So not only do we get them lining up where the pink dots are forming, but we also get them lining up in another place. And that secondary overlap lowers the energy of this transition state, which makes this transition state kinetically faster to occur. It's going to be the first transition state that occurs because it's lower in energy. This is similar to what we were saying when we were looking at kinetic versus thermodynamic control. And the reason that a reaction can be under kinetic control is because one of the transition states is lower in energy than the other, and therefore it happens faster. That's what we're saying here. There's an endo transition state, the one we're looking at, and there's an exo transition state, and the endo transition state is actually lower in energy than the exo transition state, and therefore the endo occurs more rapidly, and therefore it becomes the major product in our reaction. So here are a couple of other images here. We can see that we have the endo transition state and the exo transition state. So now we're working with a diene, cyclopentadiene. It's the same diene that we were looking at before, but now we're also looking at a dienophile that's a little bit different. This dienophile has a double bond in it. It's another cyclic compound. This compound is called maleic anhydride, and this compound here has 2 carbonyls, and an oxygen is also in that 5-membered ring, right? So it's kind of a fairly complex dienophile, but the point is it has that double bond that's going to react in the Diels-Alder reaction. We can see those dotted lines. That's the same double bond that we've been looking at in all of these dienophiles. And it also has electron withdrawing groups. Both of those carbonyls we can consider as electron withdrawing groups, which lowers the energy of that orbital, which promotes this reaction. And when we think about those electron withdrawing groups, not only do they lower the energy of that orbital, they also have pi orbitals themselves because they're double bonds. C double bond O. It's a carbonyl. It has pi orbitals just like the ones that we're looking at. So when we consider these two transition states, the endo transition state and the exo transition state, we can see that in the endo transition state, the only difference between endo and exo in these two images is either the oxygen in the ring is pointing to the left and it's kind of underneath the diene, or the oxygen in that ring is pointing to the right in the exotransition state. So if we compare the atoms bumping into each other, the steric hindrance, it sure looks like the exotransition state has less steric hindrance. All those atoms are kind of out of the way. And in the endotransition state, that oxygen atom is right underneath the diene. It seems like that's a more crowded transition state. And indeed it is. The endotransition state has higher steric hindrance because all of those molecules, all of those atoms are right on top of each other like two pieces of bread in a sandwich. Right? They're sitting right on top of each other, which is a crowded situation. The exotransition state is less crowded. So in terms of steric hindrance, the exotransition state has less steric hindrance than the endo. So we would assume that the exotransition state is lower energy than the endotransition state. So at first, the outcome of this reaction seems counterintuitive, because we have what seems like a higher energetic state, the endotransition state, seems to be preferred. So if we only consider sterics, that's true. But what we just explained in the previous couple of slides is that this is not only a steric argument, this also has to do with orbital overlap, that secondary overlap. So we have two sources of energy when we look at a transition state, the energy of a transition state. We can have steric hindrance, which can cause some problems when atoms bump into each other, or we can have electronic interactions, which can either be destabilizing or stabilizing. And in this case, because those orbitals have the same symmetry and they can overlap in that endotransition state, those orbitals are actually a favorable interaction, and that's actually lowering the energy of this transition state. So in terms of sterics, exo has the least amount of steric hindrance. But in terms of electronics, the endotransition state has lower electronic energy because of the secondary overlap in those orbitals. So because of that, the endotransition state is actually lower in energy. That the electronic interaction between those orbitals in the endotransition state is more stabilizing than the steric hindrance is destabilizing. So overall, when we compare those two different factors, sterics and electronics, the endotransition state still wins out as being the lowest energy transition state in this case. So here's another image where we can see these orbitals overlapping. Notice how we have these green dotted lines. These green dotted lines are showing us the new bonds that are going to be formed in the Diels-Alder reaction to make our cyclic compound. So those are the two bonds that we always form, the ones with the green dotted lines. But notice how in the endotransition state, which is the one on the left, where the two molecules are interacting as if they're pieces of bread in a sandwich, and they literally sit right on top of each other. There's a lot of crowding there, but because of the orbital symmetry, you can see that red dotted line that says secondary orbital overlap. That red dotted line is drastically lowering the energy of this transition state. So we have orbital symmetry between the two orbitals that are going to form the new bonds, primary orbital overlap. Those are actually going to form new bonds. That red dotted line is not going to form a new bond. But in the transition state, because those orbitals line up and they can sit on top of each other relatively easily, that lowers the energy of the transition state, which is just to say that there are two different ways these molecules could line up. One, if they line up one way, we get the endo product. If they line up the other way, we get the exo product. And we always get the endo product because this interaction that we're seeing, the secondary orbital overlap, is so stabilizing that it favors this transition state. It's a lower energy transition state, and so this is the one that we see. We don't see the exo transition state, therefore we don't get the exo product. The major product in these reactions is the endo product. Okay, so here are some just the outcomes of some of these reactions. So we have a cyclopentadiene as our diene, and then we have this green compound that has our double bond that will serve as the dienophile, and our electron withdrawing group, which in this case is an aldehyde. It's that carbonyl. So the aldehyde has a double bond, has p orbitals, has pi molecular orbitals. Therefore, that carbonyl is going to line up in an endo transition state, and they're going to line up like pieces of bread in a sandwich, and that carbonyl group is going to end up essentially underneath the diene in the endo position. It will not be in the exo position. It will always be underneath the molecule in that endo position because of that secondary overlap. And again, we've got on the bottom cyclopentadiene and maleic anhydride. And that double bond again in the green compound in the maleic anhydride is going to serve as the dienophile. And those carbonyls are electron withdrawing groups. So those carbonyls are going to end up underneath the diene as if they were pieces of bread in a sandwich, and they're going to be in the endo position because of that secondary orbital overlap. So again, we get we've now seen Diels-Alder reactions with a 5-membered ring, and that gives us that bicyclic compound that has a point on the top. But here is a diene with a 6-membered ring. This is not cyclopentadiene, this is cyclohexadiene, because now it's a 6-membered ring. So our diene now is a 6-membered ring, which is still fine because it still has 2 conjugated double bonds, so it's still a good diene. And our dienophile now is that same one we saw on the last page that's got a double bond but also an electron withdrawing group, which is the carbonyl in this case. And so now when these two come together and make a bicyclic compound, we don't get that point on the top of where the cyclopentane was. Now it kind of looks like a little bridge, because now we have 2 6-membered rings butting up against each other. The 6-membered ring we started with, the cyclohexadiene, and the new 6-membered ring that we just synthesized from the Diels-Alder reaction. Excuse me. But again, regardless of the structure of our diene, that electron withdrawing group is always going to end up in the endo position, not the exo position. You can see that the compound on the right there, on the far right, that has the aldehyde, the CHO, is pointing up in the exo position. That is an unfavored product. The favored product has that electron withdrawing group in the endo position. Okay, and finally, if we look at this reaction on the bottom, this is what we're getting into next at the end of this chapter here, which is our diene can have other groups, other branches on it. In this case, it has 2 methyl groups. We have a methyl group that is pointing straight up on the top of that compound, and we have a methyl group that is kind of pointing out and to the right on the bottom of that compound. And where those groups are going to end up in the final product has to do with the way that this transition state unfolds. So notice that if we focus on that top carbon where the CH3 group, the methyl group, is pointing straight up in the blue compound. Now look over at the product that we just created. That blue methyl group is now a dash. So in the starting material, it's a methyl pointing straight up, and in the product, it is a dash, which means it's basically pointing down, right? And if we look at the other carbon on the bottom, now the H and the CH3 are kind of flipped, right? The H is occupying the position that points straight down, whereas on that top carbon, the CH3 is occupying the position that points straight up, right? So if we now focus on that bottom carbon of the diene, that methyl group and the H have kind of switched positions relative to that top atom. So if we look at the consequence of that in the product, we have that methyl group on the bottom is pointing straight up on top of our ring. And so the methyl groups have opposite orientation in the product because those methyl groups had opposite orientation in the reactant, right? If that methyl group on the top was pointing straight up and the methyl group on the bottom was pointing straight down, then both of those methyl groups in the product would be dashes. So we have this reaction is a syn stereochemistry, which means that when both groups add, they both add to the same side of the molecule. So whether we're going to get a cis product or a trans product has to do with the relative orientation of our dienophile before the reaction begins. So let's look at the top box on the left. We have our butadiene, our diene, which just has 4 atoms. It's a simple diene. And then we're reacting that with this cis dienophile. So notice it's cis because both of those groups, those are esters with the carbonyl, both of those esters are on the same side of the double bond. So that's cis. So after the Diels-Alder reaction occurs, not only will that carbonyl be in the endo position, but because both of the groups are on the same side of the double bond, they'll both be in the endo position, and they'll both be dashes in this case. So we'll get a cis product. We have a cis starting material, we get a cis product. If we look at the next box on the right, we still have the same diene, but now we have a trans dienophile. And that trans dienophile has those ester groups on different sides of the double bond. And so one of them is going to end up in the endo position, but the other one can't be in that same position because they're on opposite sides of the molecule. So notice how our product in that reaction is trans. One of the esters is a dash, the one on the bottom, and one of the esters is a wedge, the one on the top, because our starting material had a trans double bond and those groups were on opposite sides of the double bond. They're also going to end up on opposite sides of the product. So we'll get one ester group that's a wedge and one ester group that's a dash. Okay, so now let's move on to the bottom boxes. The bottom boxes are showing us the effects of having those methyl groups on the diene in different positions. So this is what I was saying on the last slide. We've got a methyl that points straight up on this bottom box on the left, bottom left. We have a methyl group that points straight up on our diene. On the bottom carbon, we have a methyl group that points straight down on our diene. In those positions on the diene, then they're going to end up as dashes. They're both in the same position on the diene, so we would consider that to be kind of a cis orientation because they're both the same, right? So then in the product, they're also going to be the same. If one is straight up and one is straight down on a reactant, then in the product, they're both going to be dashes. And they are going to be dashes because this is, again, taking into account the endo rule. So because our dienophile is a triple bond, we don't see the endo rule in this one because that triple bond turns to a double bond, and so we don't have wedges or dashes on those esters. They just are now flat on an alkene. But the position of those methyl groups in our diene is always the same. So when we have groups that point straight up and straight down, they become dashes. Any of the groups that are pointing straight up and straight down on our diene become dashes. Now let's look at the next example. I have a methyl group that points straight up on the top carbon. That's going to be a dash. But on the bottom carbon, I have an H that points straight down. So that's going to be the dash on the bottom carbon. Any of the groups that occupy that position that points either straight up or straight down on the diene, they end up as a dash in my product. So just to reiterate on that first example, we have methyl in the up and down position. Therefore, methyls are dashes on our product. In the next reaction, I have a methyl in the up position, but an H in the down position. So I've got a dash methyl up top, but a dash H on the bottom. So the other position that we might call, in this case, equatorial, because it kind of looks like, if we're thinking about axial versus equatorial, the ones that point straight up and straight down are kind of analogous to axial. The ones that point straight up and straight down are like axial if we're looking at a cyclohexane chair. And the ones that kind of point up and to the side or down and to the side, those are kind of similar to equatorial. Sorry. So for lack of a better term here, we'll call the ones that point straight up and straight down axial, and the ones that kind of point up into the side and down into the side equatorial. Those equatorial groups on our diene, they're the ones that become wedges. Okay, so and on our first example, the equatorial groups are both H's. Therefore, the wedges on our product are both H's. In the next example, I have an H in the equatorial position on top, a methyl in the equatorial position on the bottom. So on the top, my H is a wedge, and on the bottom, my methyl is a wedge. So there is a lot of stereochemical implications of a Diels-Alder reaction. We get stereochemistry on those atoms in the diene if we have groups on them, like we do here. We have those methyl groups. Therefore, we have to account for their stereochemistry, whether they're wedges or dashes. And we also have stereochemical implications for the dienophile, where those electron withdrawing groups are going to end up. If I only have one electron withdrawing group on my dienophile, it's always a dash. It always ends up in the endo position. If I have two electron withdrawing groups on my dienophile, it depends on whether they're cis or trans. If they're cis, they'll both be dashes. If they're trans, one will be a dash and one will be a wedge. Okay, and finally, the last concept of reactivity we have to consider for the Diels-Alder reaction here. Now we've gone over the stereospecificity, and so we can determine whether groups are going to be wedges or dashes in the final product. Now we need to look at the regiochemistry, the regiochemical implications of this reaction, which is to say that if I have certain groups on my molecules, then we will always generate a certain product where those groups end up in certain positions relative to each other but not others. This is the same as saying, like in a Markovnikov reaction, the bromine is always going to end up on the most substituted carbon. It will never end up on the least substituted carbon. So this is the regiochemistry of Diels-Alder. We'll always get a 1,4 product where in our new cyclohexane ring, those groups D and W in this case are occupy positions 1 and 4 of the cyclohexane, but they will never occupy positions 1 and 3. So the regiochemical implication of this reaction is 1,4 is favored and 1,3 is not. And so we'll get a 1,4 product in this particular arrangement of groups. And so the D in this case stands for donor. That's an electron donor. We'll talk about that more as we go on. The one that we've seen so far that's a good electron donor is when it's just an oxygen atom. If there's an oxygen atom in that D position, then we call that an electron donor, because there are lone pairs of electrons on the oxygen that can donate into the diene group. The W is an electron withdrawing group. We've already talked about that. That's usually like a carbonyl, a carbon that has some kind of multiple bond to an electronegative atom, which withdraws the electrons from that system. So if I have a donor in the position that you see in the reactant and a withdrawing group in the position you see in the reactant, we will always get a 1,4, never a 1,3. And you might think, well, all we have to do in that reactant is flip the Diels-Alder, or the diene over like a pancake. If we flip the diene like a pancake, then the D will be in that bottom position, and then we would be able to get the 1,3 product, right? How come we can't get the 1,3 product if all I have to do is flip that diene over like a pancake and then react them? Well, we'll see in the next slide. So, again, in that position where there was D, now we're calling that an oxygen atom, and specifically this is an ether. So notice how that oxygen atom, our first structure on the left there, we have that oxygen atom. You see the curly arrow from the lone pair? That's indicating that that lone pair of electrons is being pushed into the diene system. If we draw a resonance structure, if I form a double bond where that oxygen is, then that carbon that would now be double bonded to the oxygen has 5 bonds. It's breaking the octet rule. So I have to move the electrons away. The only way that I can move the electrons is where that other curly green arrow is. The double bond between those carbons is going to break and move a lone pair of electrons onto the carbon atom at the end. So look at let's just focus on the diene at this point. If we look at the diene on the left, That's its major resonance structure. But if I look at the diene on the right, you can see now that there's a double bond between carbon and oxygen, and the double bond between carbon and carbon that was there has now been turned into an anion. It's a carbanion sitting on that carbon right there. And so this is a minor resonance form, but this resonance form shows us that the carbon that's next to that electron withdrawing group, the carbon on the end of our diene that's closest to that electron, I think I said withdrawing, I meant donating. The carbon on our diene that's closest to the electron donating group, which is the oxygen, it's going to get a negative charge, which makes sense because the oxygen is donating electrons to the diene. Where do those donated electrons go? They end up on that carbon as a lone pair, and that carbon turns into an anion, right? In that resonance structure, we can see that. So now let's focus on the green dienophile. In the green dienophile, we have an electron withdrawing group. What is that carbonyl doing? The electrons are going toward it. It's withdrawing the electrons away from that double bond. Those electrons are leaving the alkene, and they're going towards oxygen. So that's why we call that an electron withdrawing group. And so when we do that, if we look at the structure on the left, the major resonance structure, we have no charges. But if we follow those curly arrows and then we look at the dienophile on the right, we notice that when the double bond moves towards the carbonyl, we're left with a carbocation on the end. And those electrons in the carbonyl end up as a lone pair on the oxygen, which is the typical resonance structure that we see with carbonyls. And so what we need to see here now is, now that we look at these resonance structures that are the outcome of having an electron donating group and an electron withdrawing group, we form these resonance structures. Now you can see that the most likely place for these carbons to react is that the minus on the diene, the anion on the diene, is going to react with the carbocation on the dienophile. We've got a negative carbon atom, we've got a positive carbon atom. So those two are always going to react together. Notice how when they do that, we're left with a 1,4 product. If I tried to flip my diene like a pancake, like I had suggested on the last slide, then we would have our negatively charged carbon would be on the bottom of this molecule, and the carbon that it would be trying to react with in the Diels-Alder reaction would not have a positive charge. So that is not as favorable of an orientation as the orientation that we're seeing in this resonance structure here, where negative can react with positive, and the negative is the outcome of being next to that donor group. The positive is the outcome of being associated with that electron withdrawing group. So when I have those two groups on the molecules in this fashion, they're always going to wind up reacting to give us a 1,4 product, never a 1,3 product. It has to do with these resonance structures here. All right, so we get a 1,4 product if the donor group is on, let's say, carbon 2 of the diene. If we're numbering those carbons in the diene, we have 1, 2, 3, 4. 1 and 4 are the carbons on the end, 2 and 3 are the carbons in the middle. If we have an electron donating group on carbon 2 or 3, we form the 1,4 product. However, if my electron donating group is on carbons 1 or 4, if it's on the end of our diene, like it is now, then we get a 1,2 product, and we never get a 1,3 product. Again, it would seem like all we had to do is flip my diene over like a pancake and then react them, and I would be able to get the 1,3. But that doesn't occur. We always get the 1,2. And so let's look at why. You might imagine it has something to do with the resonance structures. So here are the resonance structures for having an electron donating group in that position on either carbon 1 or 4 of the diene. In that case, the electron donating group, the oxygen, is going to donate electrons into the diene. We follow that curly arrow, which is going to cause the double bond in the diene to shift, which is going to cause the second double bond in the diene to shift. And so now we end up with the resonance structure on the right, where again my oxygen has a positive charge because it's donated electrons in, but those electrons were able to now move throughout the entire diene, and look, they end up on the same carbon they were on before. So we still get if we have our oxygen in position 2 or 3, or our oxygen in position 1 or 4, the outcome is the same, which is to say that we always get a negative charge on the end carbon. The carbon that's on the end of the diene will become an anion, just like it did in the previous example. If we focus on the resonance of our dienophile, we've got the same structure, right? So we're still going to generate that same carbocation that we generated in the last example. So really, this looks exactly the same. The only difference here is where that donor group is. If the donor is on carbon 2, then I end up with a 1,4 product. If the donor group is on carbon 4, then I end up with the 1,2 product, like we see here. And so this is all an outcome. This is all a consequence of examining the resonance structures. What does the donor group do to these electrons? What does the withdrawing group do to these electrons? And after we draw those resonance structures, it makes sense that we're going to line them up so that the negative carbon attacks the positive carbon. And when we do that, we always get the 1,2 product, and we never get the 1,3. So the summary here, when we look at the regiochemical outcome of the Diels-Alder reaction, the regiochemistry always gives us 1,4 or 1,2 products, depending on where that donor group is, and we will never get 1,3. The 1,3 product is not favored in this reaction. Okay, finally, the last thing we're going to talk about here about the Diels-Alder reaction is whether the reaction is thermally allowed or thermally forbidden, and whether it's photochemically allowed or photochemically forbidden. So thermal means heat, right? So when something is thermally allowed, that means that the reaction will occur just by heating it up. If something is thermally forbidden, that means the reaction will not occur regardless of how hot we get it. If a reaction is photochemically allowed, that means the reaction will occur when I shine the right wavelength of light on it. If a reaction is photochemically forbidden, that means the reaction will not occur even if I'm shining the right wavelength of light at it. So thermal just means heat, and photochemical just means light. So the Diels-Alder reaction is a 4+2 cycloaddition. It always gives us that 6-membered ring we talked about at the beginning of this chapter. 4+2 cycloadditions are thermally allowed. We don't have to shine light on the Diels-Alder reaction for it to occur. We just have to put these two molecules together and heat them up, and the reaction will occur. The 4+2 is thermally allowed. The 2+2 cycloaddition is thermally forbidden. So we cannot put two ethylenes together and heat them up and expect them to do a cyclization reaction that's similar to the Diels-Alder. That does not work. Okay, so the reason the 2+2 cycloaddition is thermally forbidden is because the orbitals don't line up right. So we went over this at length when we talked about the 4+2. We calculated the symmetry of the HOMO, we calculated the symmetry of the LUMO, and we saw that they were a good match for each other so that they could have two bonding interactions and form a 6-membered ring. However, if we do that same analysis with two membered compounds like ethylene, then we're going to look at the molecular orbital diagram again. Remember, if it has 2 atomic orbitals, it's going to have 2 molecular orbitals. The lowest molecular orbital has 0 nodes. The next molecular orbital has 1 node, and so on and so on. And in a 2-membered system, there are 2 pi electrons. So if we look at the left, this is the whole HOMO-LUMO diagram for this system because it only has 2 orbitals. And so one of them is full, it's all bonding, the one on the bottom, and the LUMO is empty. The pi star is empty, and it has all anti-bonding. If we look at the HOMO and the LUMO, their symmetry does not match. So the HOMO has 2 blue lobes on top, and the LUMO only has 1 blue lobe on the bottom. So these two cannot interact with each other the way that they are. So this reaction does not occur if we just heat it up. These two molecules don't have the right symmetry to interact in this way. So we say that this reaction is thermally forbidden. However, we can do a 2+2 cycloaddition if we use light. And that sounds strange. Why would it not work with heat, but it does work with light? Well, remember, the reason it doesn't work with heat is because the orbital symmetry is not correct. If we excite an electron in a molecule, we're changing the orbitals, right? Because remember, when we excite an electron by shining light at it, if an electron absorbs energy from light, it moves into an outer orbital and it becomes excited, right? And so we look at where these two electrons are in the ground state. The ground state is just the most stable state. So before we shine light on them, both of the electrons in this system are in that first molecular orbital, what we're calling the HOMO. They're in the pi orbital. However, if we shine the right wavelength of light at this system, we can excite one of those electrons and it will move from the pi to the pi star. That's what we see on the right. So in that case, we've changed which orbital is the HOMO. Now the HOMO is the pi star because it's the highest occupied molecular orbital. One of the electrons moved from below to up above, and therefore that is a higher energy. And so now the orbital that has been excited, now that's the highest occupied molecular orbital, that pi star. So if we shine light on a molecule, we can move the electrons around, is basically what's happening. And when we move the electrons around, or at least just move one of them, if we move one of those electrons to a higher energy orbital, then we're turning the HOMO, what was the LUMO, is now the HOMO, because now that electron has been promoted to a higher energy orbital. So how does this help? Well, if we look at the situation that's on the screen right now, if we shine some light onto ethylene, for example, some of the molecules will become excited, but not all of them. They won't all be excited at the exact same time. So if I shine some light on ethylene, some of them are excited. We'll say, let's just, for the purpose of this argument, let's just say half. That's an easy number. So half of them will have the electron configuration on the right that we see, where the HOMO is now the pi star, but the other half are not excited. So they're going to have the configuration on the left, where the HOMO is the pi orbital, and the LUMO is the pi star. So what we're going to see is that the half that have been excited now have a HOMO that has the plus-minus symmetry, and the other half that have not been excited have a LUMO that has the plus-minus symmetry. So if we look at these two halves on the screen right now, the LUMO on the left that's unoccupied can react with the HOMO on the right that is occupied because they're literally the same orbital. They have exactly the same symmetry. So if we excite some of the molecules in the sample to change their orbital symmetry, but not all of them, then the ones that are excited can react with the ones that are not excited. And then they have the right orbital symmetry, and then the reaction can move forward. So this reaction does not occur if we can't excite that electron. So this reaction is thermally forbidden, but it's photochemically allowed because I can change the HOMO and LUMO if I shine light on this system. So here's what happens, right? We've got the half of the molecules, and again, it's not going to be half. If you shine a little bit of light on a sample, there's an exceedingly small amount that are excited. But just to make it easy, let's consider half and half. Half are excited, half are not. So the half that are excited, that are on the right, they'll react with the half that are not excited on the left. We've got the HOMO on the right, that's pi star, and we have the LUMO on the left, that's also pi star. So pi star and pi star have the same exact orbital symmetry. They can now react together. We have two bonding interactions, and we can make this reaction occur if we shine light on it. Okay, so just to summarize, 4+2 cycloaddition, thermally allowed, photochemically forbidden. 2+2 cycloaddition, thermally forbidden, photochemically allowed. And so we have just gone over at length two examples, a 4 plus 2 and a 2 plus 2, but we could do other examples too. I could ask you, is a 4 plus 4 cycloaddition thermally forbidden or thermally allowed? And the way that you would answer that question is by going through the same analysis that we've just done by creating the molecular orbital diagram. And we do that by first figuring out how many molecular orbitals there are. And we do that by counting the number of pi orbitals, or sp2 hybridized atoms in the system. And then we can say at the lowest molecular orbital, the lowest energy molecular orbital has 0 nodes. And then we just add a node to each system as we go up and make sure that the nodes are symmetric. Then we count the number of pi electrons, and we fill in the molecular orbitals according to how many pi electrons we have. Then we can identify the HOMO and the LUMO, and we can see if the HOMO and the LUMO are symmetrically, have symmetric orbitals. If they do, then that's thermally allowed. If they don't, then we can see what would happen if we excite one of them and see if the new HOMO and the new LUMO are symmetric, if their orbitals are symmetric. And if they are, then we could say that that reaction is photochemically allowed. So don't be surprised if I ask you to draw the molecular orbital diagram for a new molecule and ask you whether the reaction is thermally forbidden or thermally allowed. Okay, that's it for this chapter. On Monday, we will move into chapter 16, and we'll just keep moving from there. If you have any questions, please let me know, and I'll see you on Monday.